a direct connection from a socket to the EV without any special safety. Typically, mode 1 is used for charging electric bikes and scooters. The mode 2 of charging scheme requires a specific safety system between the point of connection to the electric network and the car in charge. The system is placed on the charging cable and is called the control box. It is installed on portable chargers of electric vehicles. This can be used in public as well as in domestic sockets. The next mode of operation, mode 3, requires an EV-SE equipment to charge the electric vehicles, which is permanently connected to the electrical network. Moreover, the control box is inherently integrated into the EV-SE. Wall boxes, commercial charging points, and all automatic charging system comes under this mode of charging. Mode 4 offers DC supply directly to the electric vehicles. This requires a current converter external to the vehicle that connects the charging cable. In the figure, we can observe the AC charging modes are all on the left side to you and the DC on the right side with the socket pins. The AC charger ranges from 2 kilowatt to 22 kilowatts, and the DC chargers range from 2 kilowatt to more than 200 kilowatts. Now you can see different models of DC charging plugs from Tesla and many other manufacturers. USA and Japan have type 1 AC and type 4 CHAdeMO DC, combo 1 AC DC, and Tesla's proprietary AC connector. Europe has type 2 AC, type 3 AC, type 4 CHAdeMO DC and combo 2 AC DC. China has type 2 based AC and its own DC GBT connector. With respect to car manufacturers, Americans, Europeans, Koreans car manufacturers have adopted CCS combo, and Japanese car manufacturers have adopted CHAdeMO. As the number of EVs is growing day by day, the adoption of new technology has seen exponentially growth. Hence, the stated charging connector list is indicative and will get changed over a period of time. Now, the architecture of EV charging system, where you could see there are multi-stage charging mechanism for electric vehicles. The architecture followed in India is EV connected to EVSE, which is monitored by CMS by user application. EVSE, electric vehicle supply equipment, which connects the charger to the main electrical supply. It also offers authentication, metering, payment services, and remote monitoring. Bureau of Indian Standard (BIS) has published standards IS 17017 that covers the general requirements and safety norms for EVSEs. Charging protocol defines the type of connector that goes into the vehicle inlet, max power and voltage per connection, communication protocol, and the type of communication links. Now, next is CMS, which is Central Management System, is a cloud-based platform managed by the company operating the charging station. The EVSE communicate with the CMS to manage the user authentication or authorization, billing and rate of charging. It also enables user-defined apps to help end users to identify the nearest charging station and also reserve a charging slot and pay. Now, the smart charging concept for optimal electric vehicle integration and its advantage of smart charging. For utility distribution network operators, it helps in more hosting capacity, faster implementation, and less cost. For utility transmission system operators, it extends the limitation in system peak load and avoids the construction of additional generation capacities. For building managers, time of use tariff optimization, PV balancing optimization, demand charge management and demand limitation, load balancing and reduction of the connection fee. Now, considering the EV charging system in this country, because the manufacturers are many, so it is equally important to have EV charging standards. Now, you can see different elements and their standard type and components of different EV charging equipments or devices. This slide presents the essential charging components and their standards. The charging interface, which includes plugs, sockets, vehicle couplers, follows IEC 62196-1/2/3, the communication protocol, that is V2G/data link layer and physical signaling process, ISO 15118-1/2/3 and ISO 11898-2. The EV conductive system follow IEC 61851-1/21/22/23/24. The battery swapping follow IEC 62840. The conductive charging connection set poses GB/T 20234-1/2/3. China and the information technology safety equipments have IEC 60950-1. In our laboratory, we have a DC fast charger type 2, which is VEVC001. Generally, the DC fast charger with high power operation, the AC-DC converter, DC-DC converter and the power control circuits become larger and more expensive to keep in an onboard charger. This necessitates the implementation of an off-board charger so that it does not take up space within the vehicle, and the DC fast chargers can also be shared by many users. As we can see in the schematic, the input voltage is 415 volt AC supply. In the first step, the alternating current or AC power provided by the AC grid is converted into direct current or DC power using a rectifier inside the DC charging station. Then the power control unit appropriately adjusts the voltage and current of the DC-DC converter inside the charging station to control the variable DC power delivered to charge the battery. There are safety interlock and protection circuits used to de-energize the EV connector and to stop the charging process whenever there is a fault condition or an improper connection between the EV and the charger. The battery management system or BMS plays the key role of communicating with the charging station to control the voltage and current delivered to the battery and to operate the protection circuit in case of an unsafe situation. So, this is the input coming from 3-phase AC supply, which is a 5-wire system with 3 phases, including 1 neutral and 1 ground. This is the auxiliary battery system to operate the components in the charger. We can see that it is guarded by an MCB. From the MCB, it proceeds to the power conversion system, that is rectification and DC-DC conversion. This is the control unit that controls the charging and communicate with the BMS. Whenever any fault in charging, the control unit send the signal to the BMS to cease the charging process completely. This EV charger works on GB/T 20234.3 protocol BVC001 model. The rated input current is 25 ampere. The output voltage is 48/60/72 volt DC and 200 ampere maximum, and the load capacity is 15 kilowatt maximum. Now, the issues related to fast charging. Fast charging is quite attractive in the sense of high power charging with short duration of time or short charging times, but the fast charging power cannot be increased infinitely. That is due to 5 technical limitations. First one, higher charging current leads to higher overall losses both in the charger as well as in the battery. As the charging current increases, the effective capacity of the battery decreases as well. For example, as given in the Pucher's law. The second one, the battery C rate increases with fast charging, and this reduces the battery lifetime due to the heat produced and increased degradation due to the higher temperature. Point number 3, when fast charging takes place within a battery, the SOC of the battery can only be reached till 70 to 80% and maybe a little bit more like 85 to 90%. But this is because fast charging create a lag between the voltage and state of charge SOC, and this phenomena increases as the battery is being charged faster. Hence, fast charging is typically done in the constant current or CC region of the battery charging, and after that the charging power is reduced in the constant voltage or CV charging, that is the constant voltage charging. For any EV charger, it is important that the cable is flexible and lightweight, and for people to use and connect it to the car. With higher charging power, thicker cables are needed to allow more charging current. It is very simple. I mean, if you like to, the resistance which decides your diameter of the conductor, and based on the required power, if you like to push maximum, then probably the size of the cable need to be increased. Else it will heat up due to the losses. In the future, with currents above 250 ampere, the charging cables would become heavy and less flexible because they are so thick, so you perhaps cannot fold it as you wish so, and it is not comfortable to use at all. The solution would be to use thinner cables with cooling and thermal management to ensure that cables do not heat up quickly. That is, of course, more complex and costly than using a cable without cooling system. Now, coming to an end, to conclude in this lecture, we have learned that different types of EV charging systems available, different standards for electric vehicle charging, and its architecture followed in India based on different manufacturers across the globe. A practical demo of the components involved, its architecture and working of EV charging system is also being understood in its basic form. I hope this lecture has brushed the basics of EV charging systems, but once again I request all of you to read more literature to understand more about electric vehicle charging mechanism for better understanding. Thank you very much. Welcome you all for the NPTEL online course on Smart Grid, and today we will be discussing mainly on the execution of all the concepts that we have learned throughout the course, how it can be implemented on a hardware platform with help of an existing test bed. Now, the concern here, when we like to exercise any concept like your energy management, whether it is bit grid or islanded mode of operation, whether the system is at peak operation or off peak operation, as well as all this HIL, hardware in loop experimentation, both in control strategy as well as in power mode, can be analyzed in detail. Now, all the listeners, my personal request here, what I am going to present in today's discussion belongs to our laboratory, where we have created a very smart grid laboratory, and all my simulations results are based on the outcome of the existing lab, which is currently functional at Indian Institute of Technology, Roorkee. Now, we will be focusing on design of smart grid and practical smart grid case studies. So, first of all, see how the smart grid has been developed, and then we will take all the simulation studies into a real time simulation with hardware setup and analyze those results. Now, this is how actually the lab look like. So, I mean you can just see that this is mainly the RTDS of 6 rack, and we can say this is the power amplifier, and then we have the smart grid hardware test bench. Now, all the three, that is RTDS, power amplifier and the test bed on smart grid being connected and simulated simultaneously. Now, let us understand what are the devices currently available in the laboratory, smart grid laboratory. So, the hardware facilities available in our smart grid lab, we do have a RTDS which is of 6 rack, PB5 processor, GTAO based, GTDO based, GTDI and GTAI card based RTDS. And the very important part, the RTDS can simulate a system which is a maximum of 432 nodes. Then we have second important device to our laboratory, which is power amplifier, and the rating which is 5 kVA continuous. It can, perhaps the capacity of the amplifier can be increased to 10 kVA for a short time, and it can go as high as 40 kilovolt ampere for a few short duration of peak hours. Now, this amplifier, which is support power hardware in loop experimentation, that is PHIL, it has a high accuracy voltage and current measurement for power hardware loop simulation. It supports the AC microgrid up to 270 volts RMS in each phase. Okay. And though we do not operate beyond 250 volt at a given time, but it has the capacity, when the phase voltage goes as high as 270, still it can be made operational. Now, the DC microgrid, if you like to connect this amplifier, then it can accommodate up to 400 volt DC. Now, it has the capacity to operate in all 4 quadrant, and then finally, it has the ability to handle 0 lead, 0 lag and unity power factor operations. Now, we do have sources, energy sources. The first one is PV emulator, which will mimic your solar PV, and we have connected 2 kilowatt PV emulator to imitate the actual behavior of a PV solar. It has the capacity to accommodate the shading effect. Real world weather simulation is possible. Static and dynamic MPPT testing also can be performed with this emulator. So, as a whole, I can say 4 kilowatt of emulator in place. Now, we do have a wind emulator which can again mimic your wind renewables, and it is based on DFIG, and DFIG rated 2.2 kilowatt capacity, and it can simulate real wind simulation is possible, and we can track MPPT. That is good news. So, as a whole, if you see the PV, which is a 4 kilowatt, and the wind of 2.2, at this moment it has been connected to the test bed. Now, then we have also connected real PV rooftop of 1 kilowatt, and we also do have a diesel generator of 3 kVA capacity, single phase and push button type. So, if you see, the sources is as high as actually 4 kilowatt of PV and 2.2 for wind, and 1 for rooftop and 3 for diesel. So close to 10 kilowatt source has been connected to the test bed. So I can say it's an interesting setup which is very nicely handled 10 kilowatt capacity. Now we also do have storage sources, and the lead acid battery of capacity 60 ampere hour, and then we have ultra capacitor of 58 farad, and we can possibly investigate all type of storages. And we do connect approximately at the given time maybe 6 to 8 kilowatt of or the kVA of storage that can be connected to my test bed at any given time through battery. So as a whole, we can certainly test a test bed of 15 to 20 kilowatt capacity. Now then, coming back to loads, we very interestingly recently acquired a programmable load. I mean, it's basically 3 single phase loads, and the power rating of each device is close to 1.5 kilowatt. So total of 4.5 kilowatt load, and it can very interestingly operate at all 3 constant power, constant impedance and constant current load that can be implemented. And then going back to converters, we do have these converters are used for integration of sources as well as storage, and we have both DC-DC and AC-DC type converters, and we do have the converters which has the capability of both bidirectional and unidirectional capability inbuilt. Now, what is hardware in loop HIL experimentation? You must have heard about HIL experimentation of smart grid. You develop a concept, you simulate something, and then you try to assure, confirm your analysis or concept or validate it through an HIL experimentation. And in hardware in loop HIL simulation, hardware devices are interfaced in a real time simulator, that is RTS, which contain rest of the model necessary to test the device operation. So through HIL, we basically connect the hardware devices to your simulator, and most of the components are available within the simulator, and few hardware devices that can be interfaced with your simulator. Now HIL simulation, hardware in loop simulation, offer a very cost effective and safe method to test physical devices under real time operating conditions. HIL simulations are of 2 types. One is so called closed loop type, and the other one is known as open loop type. And in case of open loop type, it is very interesting that where the signals are sent from the RTS to the device, or most commonly, whereas in case of closed loop, the response of the device is fed back to my RTS. So we do have 2 types of HIL. One is closed loop and the other one is open loop. In case of open loop, hardware in simulation during open loop, where signals are sent from the real time simulator to the device. So we have a simulator, so signals are sent from the simulator to the physical device. Whereas in case of closed loop, the response that has been received from the device can be given back to the RTS. Now there are 2 types of HIL. One is known as control hardware in loop, and the other one is known as power hardware in loop. CHIL, control hardware in loop simulation, PHIL, power hardware in loop simulation. Now in case of CHIL, physical control or protection relay devices are interfaced with the RTS and exchange digital and or analog signals. So, there is signals are exchanged, but no power. If you see the CHIL application, the signals can be exchanged at low voltage level uh, around plus or minus 10 volts, allowing a straightforward interface with the RTDS using digital to analog and analog to digital converters. So, if you see, this is my RTDS or the real time simulator, then we convert the output from D to A, and that analog information will go to my amplifier and then to my device, which is under test. Now, the outcome of the device now can go back from analog to digital conversion feedback to RTDS. So, this kind of setup is certainly a closed loop, and it is control hardware in loop simulation with closed loop representation. In case of power hardware in loop simulation, PHL simulation involves interfacing the simulator, that is RTDS, with a power device such as a motor, inverter, generator and transformer, and the real time simulator and the power device exchange power over the PHIL interface. So, the simulator and the device do exchange power, which was not there in case of your control hardware in loop simulation, but in case of power hardware in loop simulation, the devices could be either motor, transformer, inverter, converters, and there is a power exchange takes place between your device and the simulator. Now, the digital to analog DA converter includes, as part of the RTDS, provides analog signal scaled down to electronic level within plus or minus 10 volts, and the amplifier are required in PHIL simulation to scale the signal sent from the RTDS to the DUT unit or your device unit. Now, please try to understand, in case of PHIL, we do need to have an amplifier, and that amplifiers perhaps scale up your signal received from your simulator and give the amplifier signal to the device. Now, in case of PHIL simulation, which requires complex circuitry and hardware maintenance compared to control hardware in loop simulation. Now, this is the closed loop setup of your PHIL. We can see this is my RTDS, and we have scaled and then D to A converter, and then through amplifier it has been given to my device, which is under test, and further at feedback we can have voltage and current sensors in place, and then A to D conversion, and through filter we can give that output to my simulator. So, this is a closed loop where the amplifier do interface both your RTDS and the device could be your test bed too. Now, there are different case studies we have considered for discussion for this NPTEL course, where we will talk many case studies one by one, how it has been validated through hardware setup. In previous lectures we have discussed about simulations, and today we really talk about how they have been validated through a hardware test bed or a platform through both CHIL and PHIL experimentations. Now, first of all, power flow control strategies, that is your case study 1 we will be discussing. Then we will talk about case study 2, where isolated DC microgrid operation, and then we will take care of PHIL. We will consider a case study 3, that is DC microgrid integration to IIT Roorkee distribution system, and case number 4, coordinated voltage control for IEEE 33 bus system. So, these are the 4 case studies we will be focusing in detail during today's lecture. Now, when we see the power flow control strategies, Uh, in the initial stage, I think in the previous lecture also you might have seen the DC microgrid architecture. This is my utility grid, okay, and we had GSC, and this is my DC bus. We have loads connected, and my PV, battery, and ultra capacitor in place. We have also discussed the flow chart in our previous lecture. So, depending upon the grid situation, we can control your devices within the DC grid, so that the maximum stress on the utility can be avoided by optimally operating your storage devices to meet out the loads. So, by sensing different SOC points, one can easily allow its battery whether to charge or discharge, and similarly the PV and other connected devices such as supercapacitors. We have seen that there are different operating modes have been considered. So, one could be my peak mode of operation, and the other one could be the off peak mode of operation, and then finally we can consider the isolated mode of operation. Please try to understand the main objective of having DC microgrid or smart grid in place with my existing power system is to perhaps support or help the main grid to survive better, which was not possible earlier without smart grid. So, here one of the main objective, the system is always under stress, means the utility is under stress, because they do have different load characteristics, and when it is at peak point, then certainly the system is under stress because they are not able to cater all the loads connected during that particular hour. So, now we have couple of, let us say, couple of microgrids, maybe 100 of microgrids, maybe millions of microgrid in place across the country after 5 to 10 years. So, if those microgrids, let us say, had bit of energy stored in their batteries, so instead of taking energy from the grid during peak hours, if they can survive themselves for some extent, then the grid will be completely relieved. And also during off peak hours, when the system is not at stress, so then if my battery status can be checked, and if the smart grid storage is already having huge storage, then it can manage its load, and if not, then it can draw energy from the main grid to charge the battery storages. Whereas going back to the third scenario, if the grid is not present to me, then also I can get some sort of comfort to meet my critical loads without the grid. So, that case, depending upon the storage capacity, we will keep on catering the loads, and if the battery discharge SOC is very low, maybe below 30% or below 20%, we will slowly keep on disconnecting the non-critical loads, and if required, finally, because the grid is not there, even the critical loads may be compromised. But if you do a proper design, certainly the critical loads can be protected with a hope that the grid which is not available to you is not for a very long time. But if it is completely isolated remote area, then you have to design your network such that given a period of time of your application, you must be able to manage your critical loads at any given time of the day. When we come back for the next lecture, we will talk few more applications on smart grid on hardware setup. Thank you. Welcome you all for today's NPTEL online course on smart grid. And during last lecture, we were discussing about the execution of the smart grid concept on an laboratory scale of hardware setup. We have seen the different facilities available in the laboratory, and we were talking about how a DC microgrid can be simulated at 3 different operating conditions, both at peak load conditions, off peak conditions, and isolated mode. or islanded mode of operation. Now, during this case study, I like to explain you all what kind of time intervals have been considered, the status of the devices have been identified. During the peak mode, we have considered actually different time period like 0 to T1, T1 to T2, T2 to T3 and T3, T4, T4, 5 and 5 to end. So, we have considered different time of operation, time intervals, and these are the battery status, whether it is absent or ideal or the super capacitors operation, and these are the SOC status, whether it is 70% or greater than 30%, less than 30%, less than 20%, less than 10%, etc. And we can say the grid status when it is ideal, ideal, etc. And whether it is a peak hour, yes, it is a peak hour, peak hour, peak hour, peak hour, peak hour. Now, one point let us all understand, when we talk about peak mode of operation or peak hour of operation, means my utility is experiencing a peak hour. And whatever the experimentation we have done, we have considered that at this point of time the system is facing a peak. Okay? So, the peak condition of the system has been sensed, and based on that peak hour point, we allow our DC microgrid to operate accordingly, so that my grid will not be stress mode, and similarly off peak. But still there are a bit of challenges. How do we sense the peak period, whether the peak period based on your frequency that can be identified, or based on the pricing of energy at that given time. So, that is another challenge that need to be seen. How do you like to identify the peak hour based on the pricing or based on the frequency? But what we are focusing here, if the system is at peak, how do I have my control strategy and manage all my devices not to stress more to the utility? Now, similarly the off peak and isolated mode. Now, we will get into the hardware simulation, which is very important. I need your attention, please focus. Now, the peak hour mode, we can see there are so many characteristics. I will be interested to explain you one by one very slowly. This is my time period T1, and this is at T2 and T3, T4, T4 and T5. And this is basically the DC bus voltage. Could you see the variation? This is what the bus voltages have been, bus voltage has been monitored, that is V bus. And then we can see the PV current, battery current, as well as ultracapacitor current characteristics. So, this characteristic, the green one, which is you can see this one, which is my current characteristic of the PV, and the blue one, which is the current characteristic of my battery, and the pink one is the current characteristic of my ultracapacitor. And then we will see the load which has been connected to my grid, which is the load current, which is keep on reducing. And then the main important part here, we have C6 and C7 characteristic, which is my grid voltage and current characteristic, grid voltage and current characteristics. And to see further, we have actually zoomed the B characteristic, you can see, which is the zoomed view of the first characteristic, that is A characteristic, and at instant T1. So, we have different time instants. So, mainly this area which has been zoomed, now we can clearly see how my bus voltage looks like, and this is PV current, battery current, ultracapacitor current, and further we can see the grid voltage and grid current. And we have not considered perhaps the 1, 2, 3, 4, 5 and 5 has not been the load current has not been considered in the zoom characteristic of the B. Perhaps we can see the superimposed waveform of the grid at instant t1, these two C6 and C7, the both voltage and currents have been superimposed just to understand how my voltage profile is varying and how the current characteristic is keep on varying. So, the basically the combination of these two. And perhaps the D, it is we have considered one more time instant, that is T5, and we have also zoomed this zone, that is T5 instant, and you can see the characteristics in detail, and C1 which is my bus voltage, and then we can see the PV current, battery current. The one significant here, you can see the battery current actually stepped up, and whereas it is again a step down depending upon different loading conditions. Okay, that has been considered, and then you can see ultra capacitor, and again my grid voltage and current characteristics, and those two have been superimposed just to see, and you can see the way the current characteristics behave compared to the previous one, just to understand the system perspective. And this is the way actually the peak hour mode operation being performed. And if you move to the off peak hour mode, and off peak hour mode, actually you can see this, like once again my bus voltage at off peak, and then we have the PV current, and certainly then we have the battery, and then we have my ultra capacitor characteristics, and then that is a load current which is constant, and then we have grid voltage and current characteristics. And now depending upon the different cases, like case 1, case 2, case 3, case 4, at different time instant T1, T2, T3, you can see the characteristics behave from T1 to T2, and again from T3 to T4. Now, in case of isolated mode, we can clearly see my grid is actually absent. So, when my grid is not there, that means both the C6 as well as C7 they are not present, because grid is not available to me, and it is just within the microgrid we have captured the bus voltage, DC bus voltage, and then we can see the PV current as well as battery current, ultra capacitor current as well as load current. These 5 characteristics have been tapped, and that is what actually the first characteristic A look like, and whereas the B and C are the zoomed characteristics of my T3 and T4. So, we have considered, previous case we have considered T1 and T5, now we are talking about both T3 and T4. So, this area as which has been zoomed here, and this area which has been zoomed here. So, we can clearly see especially if you focus the battery which is not varying much, sorry, the PV is not varying much, whereas the battery drop down. In case of T4, you could see the PV is gearing up, whereas the battery, which is in the same way similar to my previous T1 scenario. And above and all, when it is the grid is not available, the whole energy has to be met within the system, and certainly we have to curtail some of the non-critical loads as and when the battery SOC goes down, and step by step we can curtail the non-critical loads to manage your energy scenario. Further, we have considered a interconnection between 2 DC grids, If you remember in my simulation, we have considered two DC grid, one is at 380 volts, the other at 48 volts, and we try to control the scenario of having two DC grids. And now in case of this case study, we have considered one microgrid. They are autonomous microgrids, and during practical implementation, we have considered one grid at 48 volts and the other grid which is at 100 volts. Now, in case of inter-DC grid power flow, bidirectional power transfer between two autonomous DC microgrids, and the autonomous DC microgrid, the first microgrid allowed to operate at 100 volts, whereas the second DC microgrid allowed to operate at 48 volts. Both the microgrids are autonomous, and you can see the experimental results of two microgrids. We have considered the time zone T1, T2, T3, T4, T5 and T6. Now, for better understanding, we can see there are two VA, that is the first grid, and this is my second characteristic, that is VV, the green one. And the first one, the I1 represent my autonomous grid number 1 and I2 represent my autonomous grid number 2. So, similarly for both the grids, we can have PV characteristic for the first grid, battery characteristic for the first grid, load characteristic for the first grid, and similarly battery, PV and the load characteristic for the second microgrid. So, we do have two microgrid in place. During theory, we have discussed two microgrids are of two different voltages. One is at 380 volt, the other is at 48 volts, and the simulation strategy has been discussed. But during the practical implementation, instead of 380 volts, we scaled down to 100 volts, and the second grid is 48 volts, and then we performed both the grid simultaneously. And then one more setup where we thought of expanding the microgrid scenario to a larger scale, the impact of microgrid or a smart grid into a national grid perspective, where we assume that there are hundreds and thousands of microgrids may present in future, and what sort of impact that the national grid can visualize. We have seen if the system is at whether it is a peak condition or off peak condition, or there is no grid available to me, my smart grid has to manage its energy within itself. Now, if you take the Indian grid at large, so this is my Indian grid, and at a particular point of the one of the bus of that Indian grid, we can come down to the distribution level, and that bus we can connect our DC microgrid with help of real time simulator as well as power amplifier. Now, the same setup, closed loop setup, we have, let us say, your real time simulator, and then we have your power amplifier, then we have the device on test, all right, and further we can give a closed loop signal to my real time simulator. And I am not whereas focusing here the conversion between digital to analog and further analog to digital conversion before giving back to my RTDS. Now, this is what actually the test bed which represent my device on test, and this is what my amplifier look like, and this is what my simulator is all about. Now, the concept is the point of selection is one point of the national grid where we experiment this, and we repeat this kind of setup at each and every bus of the national grid to see the overall impact of energy management at each and every microgrid, how it can really enhance the system capability at a national level. And we have considered one case study, that is case study number 3, where the DC microgrid of our laboratory has been integrated with the IIT Roorkee distribution system. In case of reduction of the Indian network, if you look at the Indian network at large, which is a very huge, and simulating Indian network within our simulator capability is impossible. That's why we try to reduce the all India network transmission system to a reduced system, so that that system can be simulated or burned within my simulator, and at one transmission bus, scaling down the voltage to a distribution bus, we can integrate the IIT Roorkee network, and further within the IIT Roorkee network at one bus electrical engineering department, we can integrate our DC microgrid and see the overall impact, changing the behavior of your DC microgrid control by adjusting both battery, ultra capacitor and PV emulator as well as load, how we can see the impact of managing the peak scenario faced by the utility or the system. Now, we have considered the all India peak of 2013 during the month of August, and we found that over 280,000 circuit kilometer of the transmission network at different 5 zones. And truly, the Indian network, which had 6,034 buses, out of which 575 buses had generators and 3,422 buses had loads, and altogether there were 8,116 transmission lines. And simulating such huge network having 6,000 buses were impossible. So an attempt has been taken by the research team of this laboratory to reduce that network to a smaller scale, so that at least we can simulate the all India network with the simulation capability available in our laboratory. Now, the net generation at that point was 120 gigawatt approximately, and the load was 117 gigawatt. Now, this is how my network looked like. So, this is the original all India network, which had approximately 6,000 buses, and this network through rigorous simulation have been reduced to a network of 120 nodes with 216 lines. So, what we have done basically, each and every zone have been squeezed to a single node based on certain algorithms, and then now my all India system is being represented by 216 lines and 120 buses. So, it is easy for me to simulate 120 bus all India network instead of going for 6,000 buses at large. We have also analyzed the feasibility study of DC microgrid integration to IIT Roorkee distribution system, and the practical IITR distribution system is modeled within RTDS, and we have taken the practical data of IIT Roorkee system and simulated within the RTDS, and you can see without the DC microgrid and DC microgrid interfaced, you can see the different voltages at different buses of the network, and it has been felt that having DC microgrid interfaced, certainly we can improve the voltage profile of the system. A significant improvement at bus voltage profile and effective utilization of PV is observed with help of DC microgrid integration. Optimal power flow of the lines is also achieved by optimizing the placement of DC microgrid. The DC microgrid can be placed at different locations. So, by varying the location, we felt that optimal utilization of the lines as well as the voltage profile can be achieved. it is a runtime window of IIT Roorkee system. I mean, this is what the pictorial view of IIT Roorkee campus, and this is my network. We can see this radial, but we have many rings in between. And this is without the DC microgrid. And then further, actually, we have integrated DC microgrid and carried out a PHIL experimentation of IIT Roorkee campus along with DC microgrid interfaced. We have also performed a couple of case studies on coordinated voltage control, and in which we had the utility, which is the utility grid. Then we have taken a distribution system of 33 bus, and then you can see the DC microgrid which has been interfaced to a IEEE distribution system and connected to my utility. And the DC microgrid, which is 1.7 megawatt of load, and then 0.4 megawatt of battery and 1.8 megawatt of PV, which is at the simulator level, but they have been scaled down 1,000 times to realize in the laboratory scale. And this is what the setup look like in the laboratory. Just to emphasize, you can see the RTDS here, amplifier, we have PV emulators, DC loads, battery and ultracapacitor, DC-DC converters, sensors, DC-AC converters, oscilloscopes, and transformers. This experimentation, the very interesting part, as I told you, this is the amplifier, and the signal which has been fed to my setup, which is the device under test, after receiving the signal in the digital form, and then we convert that D to A, give to my amplifier, and then feed back to my system, and then the further analog to digital conversion, and it can be given back to my RTDS. So, this is basically a closed loop PHIL experimentation setup. And once again, similar to the previous discussions, we can see the characteristics, power characteristics for both PV and DC microgrid. The proposed voltage control, then existing and without CVC, different comparisons. So finally, it has been claimed that with help of DC microgrid, certainly the coordinated voltage control can be achieved better compared to a system without having a microgrid. With this, we come to an end of today's lecture. Overall, I like to emphasize that we have discussed on the hardware implementation of the cases that have been discussed earlier during previous lectures, where we simulated many case studies. Then we took those concepts or ideas into simulation level first, and then we executed on a hardware setup. Though there are a bit of challenges, but fortunately all the simulations for energy management and then integrated with the IITR Roorkee distribution system, interfaced with All India network and coordinated voltage control schemes have been very perfectly executed with help of a DC microgrid in place. Thank you very much and good luck.
Okay, so good evening, everyone. So now we have concluded the day 17 classes. So we'll continue it tomorrow also, and meanwhile, maybe on Thursday or Friday, we will float the second quiz, which you may answer in next 1 to 2 days. We will update it on WhatsApp group and WhatsApp group also, and we will tell when we will float. And maybe by Friday we will complete this course, and then we'll try to get with us on Friday, and then conclude the things which we have not directly contact which we have seen, because the mostly part was demonstration only. So now we'll meet tomorrow 5 p.m. Thank you.